Bismillahirrahmanirrahim. We are starting the new session, and if you remember, we finished with 8th formula. We finished with formula number 8. So now I am starting with formula number 9. So that will be proved by you. I will give you the answer of that. I proved formula number 8, that is Laplace of e power at Laplace of e power at into sine bt, and I showed you that it is always equal to b upon s minus a square plus b square. So in the same way, you will prove that Laplace of e power at into cos bt will always equal to s minus a over s minus a square plus b square. Then in formula number 10, you will show that e power at into sine hyperbolic bt will be equal to b upon s minus a square minus b square. Then formula number 11 is e power at into cos hyperbolic bt will be equal to s minus a upon s minus a square minus b square. And finally the formula number 12 will be Laplace of e power at into t power n will be equal to n factorial upon s minus a power n plus 1. So these are the formulas which will be used very frequently in coming questions. So now I am going to solve some of the questions which are directly related to these formulas. So let's write few examples to show that how these can be solved. Again, I am writing few examples. Find Laplace transform in the following cases. Number 1, Laplace of t cube into e power minus 2t. Number 2, Laplace of t into sine 3t. Number 3, Laplace of e power minus t into cos square t. Number 4, Laplace of e power t into cos hyperbolic 2t. Number 5, Laplace of e power iota t into sine hyperbolic t by 2. So now we will go through all these examples one by one. These are the direct formulas, or these formulas can directly be applied on these questions. So Now starting with example number 1. So in example number 1 we have Laplace of t cube into e power minus 2t. If you look at this example, it is directly related to formula number 12, because we have in formula number 12, you see this is formula number 12 and this is exponential multiplied by t, and we have exponential multiplied by t. So we will directly apply this formula. So as per this formula, we need to write n factorial. Here n is 3, so 3 factorial divided by s minus a is minus 2 power 3 plus 1. So it will be equal to 6 divided by s plus 2 whole power 4. This is the one way of directly using this formula number 12. But there is another method which is preferred to use, and in this method we need to use first shifting theorem. What is the method? This is the question. So leave the exponential and first find Laplace of t cube. Means without exponential, leave the exponential there and find the remaining term, Laplace of the remaining term. So we know that Laplace of t cube will be equal to 3 factorial upon s power 3 plus 1, means 6 upon s power 4. Then write exponential and from exponential pick the value of a. Here a is minus 2 and subtract that value of a from s. So s minus a, which is the same value 6 upon s plus 2 whole power 4. So this is the preferred way to do this. Otherwise, if you know directly the formula, then you can use direct formula as well. So now coming on to example number 2. In example number 2 we have Laplace of t into sine 3t. Now it is a product, but we do not have any exponential term in that product. And till now, if we have a product without exponential, then it is not possible for us to give the Laplace of that particular term. So it is mandatory for us till now that we do have at least one exponential term. So now I like to induct exponential, so we can write the value of sine 3t in terms of exponential. So if I write e power iota 3t minus iota 3t upon 2 iota, then it will fulfill my requirement. That is the induction of exponential. So now I can rewrite 1 upon 2 iota, then Laplace of, it is become t into e power 3 iota minus t into e power minus 3 iota. So you will find that question now again lies in this example number 1. Now it is as per requirement of example number 1. What needed is to apply formula number 12 twice. So I am writing 1 upon 2 iota, and this is here, this is 1 factorial divided by s minus 3 iota whole power 1 plus 1, and then minus 1 factorial divided by s minus plus 3 iota divided by 1 plus 1. So my final answer will be 1 upon 2 iota 1 upon s minus 3 iota whole square minus 1 upon s plus 3 iota whole square. Moving on to example number 3. Here we have Laplace of e power minus t cos square t. Now we know that if cos is not linear, then there is no way to find the value of that thing. So even though if I use the same method number 2 here, still it is not possible for me. No direct formula is possible here, and no method number 2 is other method is possible here, because this cos is cos square. So what I do first is to replace the value of cos square, that is 1 plus cos 2t upon 2. So then I have 1 upon 2 outside, and then Laplace of e power minus t plus e power minus t into cos 2t. Now I have two terms. So this term is according to formula number 2, and this is according to formula number 9. So 1 upon 2, as per formula number 2, it is 1 upon s minus a is s plus 1, and then plus this is s minus a upon s minus a square plus 2 square. So this is formula number 9 and this is formula number 2. So this is the response of example number 3. So now moving on to example number 4. Now if you look at example number 4 here, it is exactly according to formula number 11. The value of a is 1 and the value of b is 2. So in example number 11, I can directly use the e power t into cos hyperbolic 2t will be equal to s minus a means 1 divided by s minus 1 whole square minus 2 square. And likewise in example number 12, it is according to formula number 10, which is not here now. It is formula number 10 according to formula number 10. So that is Laplace of e power iota t into sine hyperbolic t by 2. So for convenience I am writing that here a is equal to iota and b is equal to 1 by 2, because b means the coefficient of t. Coefficient of t is 1 by 2. Therefore, Laplace of e power iota t sine hyperbolic t by 2 will always be equal to 1 upon 2 upon s minus iota whole square minus 1 by 2 square. The formula was Laplace of e power at into sine hyperbolic bt is b upon s minus a square minus b square. So this is the way to use next 5 formulas 11, 12, 13, 14, 15, or use shift theorem with initially 7 formulas. So now I am writing some practice problems for you on all these formulas, that is from formula number 1 to formula number 12. I am mixing the examples, so you decide yourself that which method will be useful for which particular example. So starting with practice problems. Practice problems. Number 1, no. Find the Laplace in the following cases. In the following cases. Number 1, Laplace of sin t into cos t. Number 2, Laplace of cos t into cos 2t. Number 3, Laplace of sin hyperbolic qt. Number 4, Laplace of t square into cos at. Number 5, Laplace of t cube into e power t. Number 6, Laplace of t into sin square t. Number 7, Laplace of t square e power minus t into cos hyperbolic t. 8, Laplace of t square e power t into sin 4t. Number 9, Laplace of sin hyperbolic t into cos t. Number 10, Laplace of t e power t into sin cos square t. So I have written 10 examples just to give you some practice, and as per our practice, inshallah I will upload the solutions of odd problems as well. Now moving on to next thing in this topic, now we are going to derive a new formula for the multiplication. It is possible that you might think that first shifting theorem has gave us the possibility of multiplication, but even though we need a formula for multiplication, if we do not want to use first shifting theorem, then there is a formula that helps us in solving the questions of different questions of multiplication. So the topic name is Laplace transform of multiplication of f of t, multiplication of f of t by t. So I am writing the it is e power n. I am writing the statement first. This is the topic. Now I am writing the statement of this. If Laplace of f of t is equal to function of s, then show that Laplace of t power n into f of t is equal to minus 1 power n dn dsn function of s. So the proof is, we know the formula of definition and we are utilizing the same formula, e power minus st f of t dt. I am using the same formula again. So now instead of utilizing the right hand side first, I am using the left hand side first. What I am doing, given is that Laplace of ft is equal to function of s. So on left hand side I am writing function of s in place of Laplace of ft. Right hand side remains the same. Now I am differentiating. I said this is equation 1, differentiating both sides with respect to s. I am differentiating both sides with respect to s. So if I differentiate both sides with respect to s, it becomes d by ds, function of s equal to d by ds, integral 0 to infinity e power minus st f of t dt. So now on the right hand side, now I am leaving the left hand side for a while. And this is the left hand side, d by ds fs, and then on right hand side what I am trying to do is to change the order. I am interchanging the derivative and integral. Remember that it is a property that operators are allowed to switch their places if there is no other alternative is available. So because derivative is an operator, integral is an operator, so I switch the operators, and now I am applying derivative first. So derivative of e power minus st is e power minus st, and again derivative minus st is minus t, and f of t dt. Because I am differentiating with respect to s. Then what I did, I took minus common and write on left hand side. Then on right hand side I have e power minus st t into f of t dt. It means This can be represented as Laplace of t into f of t is equal to minus 1 d by ds fs. So I proved the formula for n equal to 1. Here n equal to 1. So now from here I am taking the help that if I differentiate equation 1 twice, now if I differentiate equation 1 twice with respect to s, then what happened? We will have d2 upon ds square function of s on the left hand side, and on the right hand side we have d2 ds square 0 to infinity e power minus st ft dt. Instead of differentiating once, I differentiated equation 1 twice, again changing the order of derivative and integration. And now if I differentiate e power minus st twice with respect to s, then I will have e power minus st minus t minus t ft dt. So differentiating twice with respect to s, then I will have minus t 2 times it means instead of writing minus minus plus, I am writing minus 1 power 2 d2 by ds square f of s will be equal to integral 0 to infinity e power minus st into t square f of t dt. So it means this is Laplace of t square into f of t. So now if you look at equation 2 and equation 3, this is equation number 2 and this is equation number 3, what we observe that when we differentiated equation 1 once, we have t power 1 and minus 1 power 1 and first order derivative. When we differentiated equation 2 twice, we find that we have here 2t square minus 1 power 2 and d2 upon ds square. So this shows that if we differentiate equation 1 n times, then we have what we have, then we have minus 1 power n dn upon ds, and function of s will be equal to Laplace of t power n function of t. So this is the formula for showing the product of any t with any function of t. Inshallah, in the next session we will continue with this topic and do some examples on this derived formula as well, inshallah. So it's goodbye now from this session.